Hey everyone, my name is Evan Williams, and I'm going to be talking about our paper, Multichannel TextGraph Graph Neural Networks. When a researcher decides that they want to model text using graph neural networks, the very first decision they have to make is how to represent text as a graph. Four of the most common approaches are constituency parsing, dependency parsing, information extraction, and line graphs. Often a researcher will just pick one of these and kind of run with it. However, when they do that, they're missing out on the grammatical, syntactic, and semantic relationships that might be present inside other graphs. So our kind of motivating question was, why not use all of them? So similarly to how an image is represented by red, green, and blue channels, we kind of imagine a sentence as having multiple different channels of graphs. So we test our approach on named entity recognition. We use the Connell 2003 English dataset, which is probably the most common named entity recognition benchmark. The dataset contains 9 labels to detect people, organizations, and miscellaneous. So we already talked about vanilla graph convolutional neural networks in class, so I won't go over those again. But as you know, we need every node needs a feature representation. Our nodes are individual words, and we use average BERT representations for words to create our initial features. So for our first iteration of this, we take first order representations of our adapted multi-channel graph convolution. Second order representations, concatenate the two together, and then pool across the different graph channels, and then calculate a final output. However, this approach is problematic because it doesn't leverage local context for repeated words. To illustrate that, say we have an entity. The entity is called cat in the hat, but we have a phrase, the cat in the hat. For our final representation of the graph neural network, these are going to be the final nodes because each node can only have a single feature vector. So the cat and hat. So of course, this is a problem. We obviously need to realign the tokens in order to calculate loss, but because the first the is part of an entity, or is not part of an entity, and the second one is, this creates kind of a problem. We need to leverage local context better. So we create kind of a version 2 of our model where we jointly train with BERT. So we still calculate this pooled representation of first and second order relationships on the graph, and then we concatenate that representation with BERT, pass it through a few linear transformations, and that's our final output. So this introduces some new challenges because BERT's tokenization strategy is different than ours. So we need to both map to BERT's representations, and then we need to mask some of BERT's representations because we only want to calculate labels once for each entity. So here's kind of an example of that happening. There's a lot of masks in our model. This led to a new problem where our graph convolutional neural networks are randomly initialized, but BERT weights have already been trained. So if we start with a really high learning rate, then BERT's weights kind of just get washed out, which leads to a really bad model. So our solution is to freeze BERT layers until the schedule reduces learning rate to e to the -5. So effectively, our model is kind of fine-tuning with BERT. So here are our initial results. Our first graph convolutional neural network is one where each channel shares a weight matrix. That one did pretty badly. When we gave each channel its own weight matrix, it started doing better. And when we included BERT within our training process, we got much better performance. We actually beat the best performing graph convolutional neural network model, Graph-IE, on this benchmark, but we're still behind the state of the art, which is FLIRT is one of them, which when we re-implemented got 0.933 F1. So here we're experimenting with different inter-channel pooling operations. We find that average pooling gives the largest F1, although it's fairly close. It doesn't seem to depend too much on which inter-channel convolution or operation that we pick. We also tried Roberta instead of BERT, but sadly I'm running out of time, so thank you so much. Bye.